Hi, everyone. I'm James Cornelison, a Maria Gilbert Mayer postdoctoral fellow at Argonne National Laboratory. Today, I'm going to be giving a pedagogical talk of the challenges we face when trying to measure cosmic birefringence using ground-based TMB experiments. Before jumping in, I want to thank Sean Hotchkiss and the entire Parity Violation from Home organizing committee for the invitation. I really appreciate the chance to talk about this topic. It's super fun. And of course, thank you for taking the time to watch. I hope you find the discussion helpful, interesting, and maybe even a little fun. So, a little bit about me. I'm an experimental cosmologist who works with the Bicep Keck Array and the South Pole Telescope collaborations, where we build and operate telescopes at the actual South Pole. These instruments observe the cosmic microwave background to test models of cosmic inflation. And my main specialty is developing precision, ground based artificial calibrators, tools that help us both search for new physics, like parity violating axions, and understand how systematic uncertainties impact our inflation constraints. On that note, my colleague Clara Verges and I published a paper earlier this year with the Bicep Keck team on exactly this topic. Much of today's talk is inspired by that work, so if you want to get into all the nitty-gritty details, I definitely encourage you to check it out. So as I mentioned, today we're diving into the challenges of doing ground-based polarization calibration. I'll start with a quick introduction, basically answering the questions, what are we actually trying to do and why does it matter? From there, I'll bring us up to speed on the current state of the art, the methods we use today, what's working well, and what new ideas we're especially excited about. Once we have the big picture context, I'll zoom in on what a ground-based calibration measurement really looks like in practice, and then I'll walk through the key ingredients and challenges that come with that. And finally, I'll wrap up with a broad overview of the uncertainties we worry about, those tied with the calibration source, the telescope itself, and the calibration data we collect. To understand how we calibrate these instruments, we first need to understand the signal we're trying to measure. In this case, if the universe contains some sort of parity violation, how would that imprint itself on the light coming to us from the early universe? To get started, let's look at a very simple cartoon of a propagating photon. This blue line represents the electric field of a single linearly polarized photon, and the line connecting the origin of our coordinate system to that blue dot defines the photon's polarization direction. In this case, something like up-down. We can also add another photon with its polarization oriented left-right. Now, because photons are bosons, we're free to combine the two orthogonal linearly polarized photons if they have the right relative phase, and the result is a photon that's circularly polarized instead. And the inverse works too. So if you take two circularly polarized photons with a right phase relationship, the combination looks exactly like a linearly polarized photon with its axis determined by the sum of their fields. Now, we can make the universe parity violating by adding a special term to the electromagnetic Lagrangian, the Shen-Simons term, labeled CS here. This term ultimately introduces a difference in the speed of light that depends on the handedness of a circularly polarized photon. So if we go back to our picture of two circularly polarized photons, now one of them travels slightly slower than the other. That small difference means the effective linear polarization axis rotates as the photon propagates through spacetime. When we look at the cosmic microwave background, parity violation shows up as leakage between the polarization modes that should be parity even and parity odd. In standard lambda CDM, the EB cross spectrum is expected to be zero because E modes and B modes are sourced by completely different physical processes. But if there's cosmic birefringence, E rotates into B and vice versa if there's primordial B modes. And because those B modes inherit their structure directly from E, the EB cross spectrum becomes non-zero. Even better, this EB signal appears in a very specific and well-predicted way, which makes an extremely sensitive probe of birefringence. The catch is that instrumental systematics can create the exact same EB signal. Polarized CMB light hits our telescope at some angle relative to a reference axis that we define in our instrument's coordinate system. That reference axis is what lets us convert Stokes Q and U into E modes and B modes. If anything in the instrument projects that polarization at the wrong angle, we've essentially baked in an EB pattern into our data. So that reference axis has to be aligned with the detector's actual physical copolar axis, the direction the detector believes is plus Q. If those two axes are misaligned, the effect on the data looks identical to a birefringent rotation. In other words, the universe might be parity violating, or your detector might just be pointed a little crooked. To break that degeneracy, we need an external calibration. We observe a source whose polarization angle is already known in the coordinate system we care about, and by comparing the known polarization angle to what our instrument measures, we can infer the detector's true copolar axis and correct our reference frame. And that's the core idea behind ground-based polarization calibration. There are a bunch of different sources we can use for polarization angle calibration, and each one comes with its own pros and cons. I usually think of them in two broad categories: celestial calibrators, which live up in the sky, and terrestrial calibrators, which we build and deploy on the ground. There's no best calibrator out there. Everything involves trade-offs, but here are a few metrics that help us compare them. So there's cost, of course, and how well we can know or control the polarization angle, how similar the calibration observation is to our CMB observation, since that affects how cleanly we can transfer the calibration, and observing efficiency, meaning how long we need to stare at the source to get a meaningful constraint. Starting with celestial calibrators, bright polarized objects on the sky were a go-to method for quite a long time. They're free, their polarization angles were known well enough for the era, and transferring their calibration onto the CMB is straightforward because they're on the same celestial sphere. But we've reached a precision frontier where these objects just don't cut it anymore. The last solid, widely used celestial measurement of a polarization angle was from Polar Bear in 2014 using tau A, and even that comes with an uncertainty of about half a degree. That's simply not precise enough for where the field is heading now. Instead, galactic dust has become our best celestial candidate. It's free, it's everywhere, and because it sits between us and the CMB, it's literally embedded in the same maps we're trying to calibrate. In principle, it's perfect. The catch is that we still don't fully understand the polarization properties of dust. Independent birefringence analyses using dust keep showing non-zero signals, which is extremely intriguing, but the uncertainties in the dust models are still too large for us to confidently declare a detection of new parity-violating physics. If you want to dig deeper into the details, Patricia Diego Palazuelos and Ichiro Komatsu put out an excellent paper last month that I highly recommend. There are also groups exploring artificial celestial sources, essentially putting custom calibrators into orbit. The big advantage is obvious. You can design the source to have exactly the properties you want. But the downsides are also obvious. Anything in space is expensive and risky. On top of that, observing efficiency is low. These sources are in low Earth orbit, they move fast, and the observing windows are super short. So that means you have to observe it a lot. Projects like CalSat and Cosmocal are good examples of this if you want to learn more. Now let's switch to terrestrial artificial sources, because the community has come up with several ground-based strategies. Experiments like Planck, Lightbird, and Simon's Observatory have all used near-field calibrators, basically placing a polarized source or polarizing element in front of the telescope. The issue is the calibration transfer. Going from a near-field measurement to a far-field CMB observation introduces challenges, and there's still debate about whether all of the relevant systematics have been fully characterized. That said, the strongest birefringence constraint the community currently trusts comes from Planck, which used a ground-based near-field calibrator and validated it with tau A after launch. Next up are mast-mounted calibrators, which is what we use for the BICEP telescopes. These are fantastic for systematics control. You can build the calibrator exactly how you want. And the observing efficiency is excellent because the source stays fixed and we can observe it for weeks at a time. But the difficulty comes in transferring that calibration to the CMB. We observe the CMB at high elevations while the mast sits near the horizon, so we need a mirror to redirect that beam, and that introduces additional optical paths where systematics can sneak in. And because of their geometry, mast-mounted calibrators simply can't be used for large aperture telescopes with kilometer-scale far-field distances. Even so, we've completed the full calibration and CMB analysis for BICEP Keck, and our uncertainty is already at the Planck level with even tighter results on the way. The last method I'll mention is UAV-mounted calibrators, which is a young but very promising technique. UAVs solve some major problems. Unlike a mast, you can move them around, you can easily get them into the far field at the correct elevation with no mirrors required. The challenges are mostly practical. Battery life limits the flight time, which limits observing efficiency. Also, to keep the payload light, these sources are typically monochromatic, so you need multiple flights at multiple frequencies to map out the polarized beam. Because this method is so new, no experiment has yet produced a full CMB analysis using UAV calibration. But work from Gabriella Coppi and the ProtoCalc team earlier this year showed that the calibration systematics could be as low as 0.05 degrees, which is extremely encouraging for the future. The community has entered a really exciting era for cosmic birefringence measurements, and if we look at the history, it's pretty clear why. What I'm showing here are all the CMB-derived birefringence constraints from both celestial and terrestrial calibrators going all the way back to 2008. On the right, I've zoomed in on just the past decade. Everything in red since 2020 comes from dust-based measurements. The green point is from our BICEP analyses, where the red bar shows our published uncertainty, and the little green bar shows where that uncertainty sits now that we fully characterize the systematics. And the blue point is the projected precision from ProtoCalc, assuming Simon's Observatory reaches BICEP level noise in its CMB maps. What's really striking is that all three of these approaches, dust, mass calibrators like biceps, and UAV calibrators like protocalc, are converging toward the same level of precision. That means that any of them can end up delivering the strongest constraint. More importantly, all are now sensitive enough to either confirm or decisively rule out the non-zero birefringence hinted at by dust analyses. And as soon as one method reports a result, the others are close enough behind that a fully independent crosscheck won't be far off. So, this is exactly why it's crucial that we thoroughly understand every uncertainty that feeds into these measurements. For the rest of the talk, I'm going to be going into what actually goes into a birefringence calibration, especially in the context of terrestrial approaches like biceps mass calibrator and protocalc's UAV-based system. When we do this calibration, the question we're really trying to answer is, when light hits our telescope, how do we know the angle at which it arrived, as measured from the detector's actual copolar axis? So getting to that answer requires a bit of geometry, nothing too painful, hopefully, but we start by defining a reference coordinate system that tracks the telescope's pointing and orientation, right? So on the left, we see this is represented on a unit sphere, which is how we think about these vectors mathematically, but that isn't always the most intuitive way to picture things. So on the right, I show the same axis and how that looks on an actual telescope. So the green arrow is the pointing direction, the blue arrow marks our reference orientation, which can be set arbitrarily, as long as we use the same definition for both calibration and CMB reconstruction. The red arrow just completes the right-handed orthonormal basis. And one important detail is that these axes describe the telescope, not the actual detectors, right? And the detectors are the things that we're interested in. Because the optics redirect incoming light into different parts of the focal plane, only the detector sitting at the bore site sees that exact direction on the sky. Every other detector sees the sky from a slightly different direction and angle on the unit sphere, so each detector effectively needs its own version of this reference basis. So going back to our diagram, we move into the reference frame of a given detector by rotating the Boresight vectors, typically using something like a parallel transport rotation. After doing this, every detector has its own correctly transformed basis that tracks the reference orientation across the entire focal plane. So on the right side of this diagram shows that this looks what this looks like over the telescope's full field of view. Each detector has its own projected axes, and on the left, I've only drawn one transform basis so you can see uh, how the transport looks on the unit sphere for just one detector. Now, up to this point, we've only talked about the reference axis, but remember, this axis is arbitrary. We haven't yet defined the detector's physical copolar axis, and it definitely doesn't have to be aligned with the reference axis. So let's add that now. The yellow arrow marks the detector's copolar axis. The red and blue arrows still define the plane of polarization, and the entire purpose of the calibration is to measure the angle between the blue reference axis and this yellow copolar axis for thousands of detectors across the focal plane. And this is where the source comes in. So suppose we now look at a polarized source with a well-known polarization angle and slew the telescope so that our example detector is pointed right at it. By construction, we know the source's polarization orientation with respect to our reference axis at any given time. So because the detector's response varies in a predictable way, basically like a dot product between the source's axis and the detector's axis, we can solve for the detector's angle. And now there's a lot going on in these diagrams, so let's zoom in on just a single detector, right? So we have the blue arrow, which is our reference orientation, the red arrow, its orthogonal partner, the magenta arrow, which is the source's polarization projected onto the detector, which we know, and the yellow arrow, which is the detector's unknown copolar axis. All of these vectors lie in the same plane, so we can describe everything with angles. The angle between the reference axis and the source's polarization is phi s, which we know. The angle between the source and the detector is psi, which is the thing we measure from the detector response. And once we measure psi, we can simply add phi s to tie everything back to our reference frame. And that sum is what you'll see usually written in bicep Keck work as phi d, the detector's polarization angle in our reference frame. And that's our final result. So once we know this angle, we can properly count for it when we construct Q and U maps, ensuring each detector's orientation is correctly aligned. So I know that was a whirlwind of geometry, but fundamentally the procedure is straightforward, right? So we define our reference frame, we observe a source whose polarization you know in that frame, and then you connect the detector's response back to that reference. Simple in concept, much simpler, much less simple in practice, right? And here's where the real difficulty lies. Every part of that chain, from the reference frame to the source to the detector response, is vulnerable to its own set of systematic uncertainties. And as our precision targets get tighter and tighter, effects that used to be negligible now matter a lot, right? So small systematics quickly become fatal ones. And this isn't perfectly clean in reality, but conceptually we can group the dominant uncertainties like this, where the reference axis uncertainties come from the telescope and the pointing model, the source axis uncertainties depend on how well you've calibrated the source itself, and then the detector source angle uncertainties come from anything that contaminates or biases the calibration data directly. And it's the combination of all of these that ultimately limits how well we can measure cosmic birefringence from the ground. My plan now is to step through each of these three topics and just give a couple of examples on how we control systematics, starting with the calibration data itself. But before we do that, we need to talk about what calibration data actually looks like. I mentioned earlier that in principle, you could observe a source simply by slewing the telescope until the source sits directly over a detector. But with thousands of detectors, it's much more practical to perform wide telescope sweeps to map out the response across the entire focal plane. When we then go back afterward and figure out when the source passed over each detector. And for bicep, our calibrator is special because it can rotate around its polarization axis, and that lets us map out the detector's response as the source rotates, producing what we call a modulation curve. So to get the detector's polarization angle, we fit a sinusoidal model to that modulation curve. And the phase of that curve relative to the source's known 0 point is exactly what the psi angle that we're after. That's not the only way to do this, though. In protocalc, we still map out the detector's response, but instead of scanning the telescope, the source is moved around by a drone. Because the drone has to stay lightweight, it can't rotate the source. Instead, they take advantage of the polarization modulators built into class inside observatory instruments to recover similar polarization information. And instead of forming modulation curves, they convert their maps directly into Stokes Q and U. And the source to detector angle, psi, is then obtained simply by taking the arctangent of those two maps. When we think about systematics that affect our calibration data, the key question is, what can change the amplitude of the signal regardless of how we're extracting psi? So when we design a calibrator, we want two things. A, it needs to have a high polarization fraction to boost the signal to noise, and B, it needs very low amplitude systematics. So the angle we derive isn't biased by artifacts in the data or weird features in the fits. There are several considerations when thinking about the source output. First, CMB beams are broadband. Our instruments collect photons over a wide frequency range, and the beam shape varies across that range. The actual beam is the frequency weighted average of all of those little beams. So the source either needs to be broadband as well, or we need to take multiple beam maps at different frequencies to reconstruct the true beam. Second, the source must be bright enough to give good signal to noise, but not so bright that it saturates those incredibly sensitive detectors. And of course, the source output needs to be stable across the entire observing period. Fortunately, we have multiple options for sources. I usually group them into thermal sources, quasi-thermal sources, and monochromatic sources. Thermal sources are literally just chunks of carbon-loaded foam that emit at their physical temperature. They're inherently broadband, which is great, but they need to be heated or made very large to be bright enough, which makes them hard to stabilize. They're also not inherently polarized, so you need to polarize them downstream. Quasi-thermal sources use RF components to emit broadband radiation, like a thermal source, hence quasi-thermal, and they can be very bright, which is great, intrinsically polarized via waveguide, and extremely stable over long periods, but they're bulky, so they're not ideal for UAVs. And monochromatic sources, like gun oscillators, are lightweight, bright, stable, and intrinsically polarized, which makes them perfect for UAVs. The trade-off is that you need multiple frequencies to fully characterize the broadband beam. Because we're using waveguide and feed horns, our sources emit most strongly along their bore site, and the amplitude falls off roughly Gaussian as you move away from that direction. So another amplitude systematic is simply whether the source is pointed at the telescope. For something like protocalc, where the drone naturally moves up and down in elevation, you either need to physically tip the source to keep it aligned or correct for the dimming that occurs where it isn't. Likewise, if your source rotates, like ours does on Bicep, you must ensure that the source is properly collimated. That is, that its pointing direction is aligned with the axis of rotation. If not, the pointing direction changes as the source rotates, adding an unwanted angle-dependent amplitude variation to the modulation curve. Another major effect that impacts both pointing and rotation is the environmental housing around the source itself. Some fraction of the source's light reflects off the housing and back towards the telescope, carrying a polarization orientation that is different from the main beam. As the source points away from the telescope, the spurious polarized light becomes more significant, biasing the derived detector angles. For us, the effect was so strong that it completely blocked final unblinding of Bicep's birefringence analysis. In the protocalc case, where multiple telescopes may observe the same source simultaneously, this becomes pretty important. Because the source can only truly point at one telescope at a time, so consideration is going to be needed there. Now let's look at the telescope side of systematics that can affect the calibration data. When we make a beam map, we're convolving the telescope beam with what we hope is a point source. But because our mast-mounted source sits so low to the ground, we get stray reflections, like light bouncing off the ground and leaking into the beam map. We also see multiplexing artifacts like crosstalk, another detector signal leaking into this detector's data. For effects like these, where redesigning the telescope isn't an option, our best strategy is often to just characterize the size of the effect that fold that into the uncertainty. Fortunately, right now, both of these effects are very subdominant. Ancillary equipment can also introduce systematics. On Bicep, we use a redirecting aluminum mirror. Besides complicating the geometry, the mirror physically biases the polarization of incoming light due to differential reflection between parallel and perpendicular polarization. The good news is that this effect is easy to calculate and completely cancels out in pair difference data, which is Bicep, but if you don't do pair differencing, this can be a major problem. The lower plot shows biases of up to 0.04 degrees, which is right at the precision target for a protocalc. I also briefly want to mention polarization modulators like half-wave plates and VPMs, with the caveat that I'm not an expert since I've never worked on an instrument that uses one. Uh, these devices introduce a polarizing element into the optical chain that shifts polarized signals to higher frequencies, which separates them from unpolarized 1/f noise. And just off the top of my head, possible sources of systematics, again, with a grain of salt, include modulation leakage, where you've got imperfect demodulation, mixes a little of the wrong signal back in, variable rotation rate, any changes in half-wave plate rotation over time could matter. Cross polarization leakage. Neither sapphire half-wave plates nor wire grids are perfectly polarizing, so that's something you could consider. And geometric misalignments. Anything from a tilted plate to imperfect placement can shift the apparent polarization that is incident on your detectors. All right, next let's talk about things that affect our knowledge of the source's copolar axis, something that we ideally assume is known perfectly. These include any uncertainty on how we transfer the source's orientation to the telescope reference frame, as well as anything that might physically rotate or shift the source without us noticing. For sources like Bicep's RPS and for protocalc, the RF output is intrinsically polarized by rectangular waveguide, but we define the actual polarization using a wire grid. Wire grids are simple and robust, meaning that wires reflect polarization parallel to the wires and transmit orthogonal polarization. So in principle, to know the polarization angle, we just need to know the grid angle. The challenge is in measuring that angle and tying it to a reference that we can project onto the telescope. For Bicep, we measure the grid orientation by aligning it to a flat reference surface on the source housing and using a microscope to visually inspect the wires. We then align that reference surface to gravity using a precision level. And because all of our reference axis on the telescope is tied to gravity through star pointing, this projection is handled automatically by the pointing model. So any imperfections, microscope precision, level precision, wire thickness become sources of uncertainty. Protocalc uses a different method, which is shining a laser through the grid and measuring the angle of the diffraction pattern. This gives a very long lever arm and can be extremely precise, but uncertainties arise from the width of the diffraction beam and projection effects. If the laser is even slightly off axis, the diffraction pattern bows, adding confusion to the measurement. And the grid orientation here is tied to an onboard camera, whose orientation is then determined via photogrammetry with respect to the telescope. We also worry about anything that can physically change the source's orientation. At the South Pole, this is a big deal. For example, our mast is supported by steel guy wires, and during the summer, the sun just circles overhead continuously, heating and cooling the wires throughout the day. On the stiltmeter plots to the left, you could see swings of nearly a quarter of a degree on sunny days purely from the thermal expansion. If we weren't actively tracking the source's tilt, our calibration would be biased by over an order of magnitude in some cases. Now let's move on to ways our reference axis can be biased. These are mostly geometric effects and pointing model issues. First is the transformation from bore sight pointing to detector pointing on the unit sphere. The ideal pointing comes from the designed optics, but real systems aren't ideal. Module clocking, small misfocus, and other non-idealities mean actual detector pointing can differ significantly. If we assumed ideal pointing, the projected reference axis would be wrong, and it would bias the phi s angle that we care about, that we add to our calibration derived angle. Just like polarization, detector pointing is a measured quantity, typically using point sources or the CMB itself, and so that measured noise propagates into the detector angle uncertainty. Fortunately, the residuals are small, and the real concern is just not assuming that ideal pointing. Next is the pointing model. For terrestrial calibrators, the source is close enough that we must account for parallax, the apparent motion of the source on the sky, and the rotation of the source's polarization as the telescope slews. Our pointing model must track where pointing tilts occur, not just their magnitude. The closer the source is, the more important this becomes. For bicep 3's 200-meter distance, I found that that mislocating the tilt origin can introduce uncertainties up to 0.03 degrees, which will matter a lot in upcoming analyses. In bicep, we also have extra geometric complications because we use a mirror. We address this by observing an additional calibrator, the moon, since it's one of the only things we can regularly see from the South Pole. The moon isn't a point source, and its brightness varies in a weird, lagging way compared to its phase. But by modeling that behavior, we can track beam center bias and, crucially, monitor time-varying deformation of the mirror. We found significant pointing shifts on our timescales driven by sunlight and the weather. And these also induce a small apparent rotation in the reference axis. And it took a lot of work, but we figured it out, and now we can correct this reliably. All right, that's everything I wanted to cover. The examples I showed are just a small sample of these kinds of systematics that we worry about, but I hope they give you a sense of both the sensitivity of these measurements and the amount of care required to do them well. So to summarize, parity violation in electromagnetism shows up as cosmic birefringence in the CMB. Measuring birefringence requires breaking the degeneracy between instrument orientation and true celestial rotation signals. And we do that by establishing a reference frame and tying both the telescope and a well-defined calibration source to that common frame. And to make that robust, we must carefully track uncertainties to that effect. So we've got calibration data, and in that is RF design choices, stray reflections, and amplitude systematics. For source orientation, we've got the wire grid calibration and physical tilts from environmental effects, and telescope geometry, which includes detector pointing, pointing model tilts, and mirror deformation. And I'll leave this final graphic up as a reference during discussion. Once again, thank you to Sean Hotchkiss and the organizing committee for the invitation, and a special thanks to Clara Vergis and Annie Polish, who I work closely with on the Bicep Calibration project, and thank you for watching. I hope this talk was clear, informative, and enjoyable.